Okay, so let's work this problem. First thing we need to talk about is what is different about this problem than the previous problem we did.
It has a low distance, just not a discontinuous.
Discontinuous, that's the big thing. You'll notice that the load is not continuous across the structures. So we're going to have to write a set of equations that are valid from 0 to 12, and then another set of equations that are valid from 12 to 20. So if I had to put like a little range on there, this would be, I'd want a set of equations over this first 12 feet where the load is continuous, and then a second set of equations over this where the load is continuous. I'm still going to measure everything from the left side X. So when I go to make a cut somewhere here in 0 to 12, do you want to work the whole right side or the left side? I think the left side's a better choice for that one. So I'll indicate that with a little arrow. Now when I cut it somewhere here from 12 to 20, do you want to work the whole left side or the right side? I think the right side's going to be easier. So we'll work the right side. So this is the kind of logic I think you ought to apply as you break a problem down. Every time you make a section cut, look at both sides and see which one's going to be easier for you to deal with. In one of those scenarios, I'm going to need the reactions at A. So let's go ahead and get those right up front. So I'll start by assuming that I have a positive shear at A and a positive bending moment at A. Okay? And then I'm going to need the concentrated equivalent force here. It's a rectangle.
48.
Yeah, base times height will be 48. And the distance from A will be half the distance, or 6 feet. So that's enough to get the reactions. My drawing has got kind of crowded there. So using the whole structure as the free body, let's sum moments about A and make sure it's in equilibrium. So again, I'm using right-hand rule for my moment sign convention. So what kind of moment is this? That is a negative moment. Yes.
At 6, wouldn't that be right where the force is?
I'm sorry? Say that again?
If your cut is at 6.
I'm not cutting anything right now. I'm finding the reactions at A.
Oh, okay. That's the distance.
So I'm using the whole structure. So the next force I have to deal with is the 48, and it creates also negative moment. So that'll be 48 kips. And what's its moment arm from A? 6. And what else do I have? Way out there on the end, I've got a 20 kip force. What kind of moment does that create about A? Negative. And what's its moment arm? 20. So what is the moment at A? It looks to be negative. That's 400. That's 288. 688? I'm guessing.
Yes.
Kip feet. And it's negative. So what does that mean? What's my bending moment at A? Positive or negative? Negative. So let's sum forces in the y direction and get our shear value. So that force is up, that's a positive force. That force is down, that's negative. 20 kip force is down, that's negative. So what is the shear at A? Looks like it's 68. Positive. So I've got my reactions. Okay? So now let's look at this first purple cut that I made. And we talked about doing the left side, so we'll do that. So what values of x will this cut be good for? It's going to start at 0, and how big can it get? 12. So this will be a set of equations that are good from 0 to 12. And this is what my free body diagram looks like for that. The length of the element is x. On the left-hand side, I have my shear force acting up. That's 68 kips. I have my bending moment, which is negative 688 kip feet. I have a distributed load. What's the intensity of the load? 4 kips per foot. And then at the cut surface, my internal forces are I'm going to assume positive shear, positive bending moment. I think that's it. So what's the concentrated equivalent of that distributed load? It's a rectangle, so it's just going to be base times height, right? Base is x, height is 4, so that'll be 4x. What's the distance from the cut to the centroid of the force versus centroid of a rectangle? Half the distance, right? So what's the centroid should be? Distance divided by 2, that should be x over 2. Did I get everything? I think that's it. So let's make sure that piece is in equilibrium. So I'll sum moments. Use right-hand rule for my sign convention. We'll do it about the cut. We'll make sure it's equal to 0. So right-hand rule, this is a positive moment. The moment about the cut created by the force 4x, positive or negative? Positive. So there's the force, 4x. What's the distance? X over 2. Then I've got the 68 kip force, positive or negative moment about the cut? Negative. And what's the distance? X. And then I've got this moment, 688, with my sign convention, that is positive. Solve for the moment. And what do I get? This term becomes x squared, 2x squared plus 68x minus 688, and all those terms should add up and have units of kip feet. So there's my moment. Can I check that anywhere? Do I know the moment anywhere between x and 12? Yeah, what's the value at 0? I know the moment at x equals 0 is negative 688, and that should be kip feet. And when I plug in x is equal to 0, what do I get? Negative 688. Do I know the moment at 12? Not beforehand, I don't. I mean, I can compute it by putting x equal 12 here, right? But I don't know what it is just by looking at it. So I have to stop there. So now let's find the shear force. So I will sum forces in the y direction. Assume up is positive, make sure they're all in equilibrium. So starting with the shear is down, so that's minus. My force 4x is down, that's negative. 68 is up, that's positive. So it looks like my shear force as a function of x is 4x plus 68. And all those terms should be in force, in this case kips. Now remember our little thing that we noticed last time, that it looked like we thought the derivative of the moment was equal to the shear? Is that true? It is true. That makes me feel good. You have a question, Mr. White?
For like second time on the test, we feel really comfortable after we find the moment and just take the derivative.
You could.
You're not gonna, you wouldn't count on it.
No, but I would if you got the moment wrong.
Right.
So it's kind of like you're doubling down that you got your moment right. I would suggest that you do this because it's not that much effort, and then when you get this relationship valid, that should make you feel good. You could totally botch the moment, correctly take the derivative, and totally botch the shear. All right? I think that's a safer path to increase your likelihood of success. Unless you're super confident, which I know you guys all are, that you got your moment right. Do we know anything about the shear? Can we check that? Do we know the shear anywhere between 0 and 12? I say we do. I say we know the shear at x equals 0. What is the shear at x equals 0? 68. So if you put in x equals 0 into our equation, what do you get? 68. Oh, I got all kind of green checks going here. I feel pretty good about 0 to 12. Am I done? Unfortunately, I'm only halfway done. So what have I got left? I've got the group from 12 to 20. So my next set will be from 12 to 20. Can I use these equations to evaluate the shear force and bending moment from 12 to 20? Well, I can. Will I be correct? I will not. Right? So these are only correct in this range. Although you can put in any number you like in there, and it will give you an answer. It will be incorrect. So remember, I'm going to do this left piece. I'm sorry, the right piece. So there's my free body diagram, and there's my applied load. Now, just so you can see this, I'm going to remind you that we're measuring x from the left to the right. So what would this piece of the element be? I think we already talked about it before. What would it be? It would be the length, 20, minus x. Do you guys see that?
Yeah.
Because when I add these two together, when I add x to 20 minus x, what do I get? 20. The length is always 20. So now, on this cut, I put my